Hello, and thank you for joining us on our webinar today. My name is Tyler Reed, and I'm the CamWorks Product Specialist here at GoEngineer. Today we're going to be talking about 3D printing at GoEngineer HQ. Very recently, in our Salt Lake City office, we opened up a space dedicated entirely to 3D printing. So we're going to be doing sort of a digital tour through that. And then in the second half of the webinar, we're going to step through a scenario that I came up with to utilize 3D printing to solve a problem I have at home. So as I just mentioned, our Salt Lake City office just opened up a new dedicated 3D printing lab. By opening that, we joined our Dallas, Houston, Woodland Hills, and Santa Clara locations that also have dedicated 3D labs. And the reason why we did this is we wanted to showcase all of the machines that we represent and give a chance for our customers, like you, to come in and check them out in person. 3D printing is something that we're hearing about from every outlet today, and it's for many people, it's a technology that's still slightly removed from reality. Okay, so we wanted to give people a chance to come in and actually look at the machines in person, hold the parts that we've printed in person, and give us a chance to talk to you about how 3D printing might incorporate into your business or a potential idea that you have. Right? So if you're near any of these offices, or if you ever travel near any of these offices, give us a call, and we can set up a time to come in and help you take a look at this emerging technology. So what is a dedicated 3D printing lab? Well, these are areas that house CAD workstations, printers of all sorts, and post-processing areas. So an area to actually deal with the parts when they come off the machine. In our Salt Lake City office, we have a Fortis 250, which is part of the Fortis production series. We have an Objet 30 Pro, which uses the PolyJet technology to create some very high resolution prints. We have another 250, and then there in the background we have a Uprint SC Plus. And then in the front of the room we have a Fortis 400, which is the most recent addition to our lab. The Fortis 400 is a big monster of a machine, and we feel very lucky to have it in our office. Also in that same room we have a Mojo, which is the desktop FDM printer from Stratasys. We have a post-processing area, and this is the area where we clean up the parts off the PolyJet and the FDM machines. So towards going from right to left, we have a little water jet cleaning station. Underneath that counter is an electric pressure washer, and it's piped up into that white container there, and we use that to squirt off the support material on the PolyJet prints. Okay, and then in the middle there we have a detergent bath that we use to wash away the soluble support on the FDM prints, and then we have a sink to kind of clean up after ourselves and store. You can see there in the background we have some prints stored there. Depending on what time of day, it's usually kind of full with parts over there. Here's a little peek inside the washing station, and you can see on the right hand side we've got the main water jet line that we use, and then on the left hand side we have what we like to call the blue whip of death. It's a little bit higher pressure, and that thing really whips around once you lose control of it. Close-up of the sink area, you can see some prints that we've done. Nice little PolyJet print of a character from Toy Story. Lots of chains there, some lettering that we're going to be putting up on our walls, and then looks like a customer service bureau part. So, like I just mentioned, we do have some service bureau parts there. We use this dedicated area somewhat for service bureau parts, but mostly it's to print benchmark parts. So parts for potential customers who want to buy a machine but want to actually test the technology and make sure that the parts that we can print are going to be useful for their application. we'll go ahead and print benchmark parts for people in that situation. Here's some examples of some parts that came off the machines. On the left there you got it looks like a chest rook. Pretty realistic there. One of the interesting details that you can't see is that there's a spiral staircase inside that rook. So that's something that you wouldn't really be able to manufacture using a subtractive method. That would have to be cast. And then we have a mouse there, and the mouse has obviously been post-processed. On the bottom half it's been painted, and on the top half it looks like it's been vacuum metallized. So those parts came off the FDM machine, were sanded, there might have been a little putty applied, and then they were painted or plated. Here's another print off the FDM machine, and this is kind of a close-up so you can see how much detail you can get out of these prints, right? And this is a very organic shape, so this is a perfect shape that is manufactured using 3D technology or 3D printing technology. Just in terms of the shape being so organic, really lends itself to additive manufacturing. Here's a part being printed on the Objet Pro. This is a Halo Master Chief character. You can see this is mid-print, so or not mid-print, it's actually near the end. It looks like he's just got the tips of his visor left to finish there. So you can kind of see the support material resting under his back. There's a little bit of a difference in color there. These are going to be, this is done in the clear, so it's not completely translucently clear until there's a little bit of post-processing done, just a slight bit of sanding. This is also a part that came off the Objet, again with the clear material. This is something that it almost looks like glass or ice to me. That's a unique characteristic of the Objet prints and the PolyJet technology. This is very fine detail. So this material here prints in 16 micron Z layers. Okay, so that's about 6/10 of an inch, 6/10,000ths of an inch. Okay, so you get some very fine detail that you wouldn't really be able to get out of the FDM machines. So these are always fun to look at. PolyJet technology lends itself more to precision and fine surface finish. So for people who are printing parts more for display or for marketing purposes, things that are going to show up in brochures or expos, PolyJet technology is a great technology to look into. So I wanted to just talk a little bit about each machine that we have there in the Salt Lake City office. This will give you an idea if you do come to us for Service Bureau parts, or if you want to do a little bit of research on these machines yourself before you come in and check them out. These are the machines that we have. So we saw a brief picture of each one. We got the Mojo, which is that desktop machine. It literally sits on a desktop. This is meant to be a very compact yet professional desktop printer. Okay, it's going to be a plug-and-play unit just like a regular laser or inkjet printer is. This is going to be something that can actually fit right inside your cubicle. So I know myself as a designer in the past, having something there that could allow me to print jigs and fixtures very quickly and without having to deal with anybody else would have been a godsend. This does use the FDM technology. It prints in ABS and soluble support. The work envelope is 5 inches by 5 inches by 5 inches. The layer thickness is actually 7/1000ths, which is pretty good in comparison to some of the mid-range printers. And the software is Print Wizard. It's very simple to use software. Next we have the Fortis 250, and we actually have 2 of these in the office. This is a production series machine, but with the simplicity of a desktop machine. It's a pretty well-rounded choice for people who want both prototype parts and limited run end-use parts. It does use FDM technology, prints in ABS Plus in many colors and soluble support. The work envelope is a little bit more than twice as big as the Mojo, so it's 10 by 10 by 12 inches. In the layer thickness options we have are 13/1000ths, 10/1000ths, or 7/1000ths, and the software we use is Insight. So this actually offers several layer thicknesses, which helps you balance out time to print with resolution in the Z, smoothest of the part. The big daddy there is the Fortis 400. So this is an advanced heavyweight printer that's capable of large builds in production grade materials. Okay. This is going to be recommended for some of the most demanding applications in terms of strength, stability, size, and also low volume production manufacturing. Okay. This, along with the 900, are the pinnacle FDM printers out of in the Stratasys line. It's going to print many materials. It can be outfitted to print ABS, polycarbonate, some combinations of the two, PPSF and Ultim, which are two high performance, high temperature, high strength materials. It can do soluble and breakaway support. The work envelope here is 16 by 14 by 16 inches, and the layer thickness options are the same as the 250, but we also have the option to print in 5,000ths layer thickness now as well. So we can get some very extremely fine prints out of this 400 that are physically large. We can print something the size of a football helmet very easily. And then the last machine we have here is the Objet 30 Pro. This is also a desktop printer, but this is going to be a desktop PolyJet printer as opposed to the FDM printer. And like we discussed in the previous slide, this is going to be capable of some extremely high definition prints down to 16 microns layer thickness in a variety of materials. So the materials actually come as resins. Okay, we call them digital materials, and they are digitally mixed. So as opposed to FDM technology where you have a spool of ABS plastic or polycarbonate, these are resins that are mixed very similarly to a cyan, yellow, magenta ink setup. Okay, where with those three colors, an inkjet printer can obtain millions of different colors by mixing them in the correct order, right? Same sort of thing here with the Objet 30 Pro. We have a certain set of resins that can be mixed, and they can be mixed to obtain very clear and rigid materials, very opaque and rubbery materials, and everything in between. Okay. The support is kind of gel-like or waxy and is just blasted off with the water jet. The work envelope here, they give it in metric units, so here in inches it's a little bit precise. It's essentially the size of a piece of paper, 6 inches tall. Okay. The layer thicknesses we have available to us are either, like I mentioned, 6/10,000ths of an inch, which is 16 microns, or up to about 32 microns for some of the other materials. The software we use is Objet Studio. Okay, so that about does it for the digital tour. Like I mentioned, if you're near Salt Lake, or if you're ever going to be traveling near Salt Lake, or if you're near one of our other offices, Dallas, Houston, Woodland Hills, or Santa Clara, go ahead and either just stop by or call ahead of time and make sure somebody's around to actually show you the machines, but we'd love to have you come in and look at them. Alright, so for the next half of this webinar, we're going to go over this scenario I came up with. It's actually a true story. So the whole scenario is that I'm a homeowner, which means I have problems, right? I think a lot of people can relate to that. I'm also an engineer, which means I have solutions, or I think I have solutions, right? And then I'm also a business person, which means those solutions I usually like to make a profit or make some money off of. Okay, so with those in mind, the scenario that I'm facing is that inside my home I have some I-beams that are about 12 feet high, okay, and they're collecting dust. And you can imagine with ceilings that high, I also have light fixtures and neon signs and all sorts of things that are collecting dust up high. So the issue that I have is that my vacuum and my arms don't really allow me to reach up that high to clean. Okay, so that's the issue that I'm facing. So we're going to walk through, I'm going to approach this as an engineer and walk through the typical solution development cycle that I'm used to seeing. Okay, so step one is usually conceptualize the issue and conceptualize a solution. Okay, this is going to be your napkin sketch stage. And we're going to design our solution. In my case, this is going to be done in CAD, but this, again, might be something that you do with pencil and paper. We're going to validate our design. And a lot of times at this point, the validation step, you find that things aren't actually coming out the way you want them, so you step back either to the conceptualized stage or the design stage, so there becomes a bit of a loop here, right? Once it's done validating, then you document, you create your manuals, right? And then you actually manufacture and release the product. Okay, so that's your typical solution development cycle. For now, I'm just going to go over the first 3 steps, because that's really where 3D printing and the other solutions that we represent come into play. So the first step there was conceptualize, and my concept here you can see in my little notebook sketch is I'm going to create an extension on my vacuum that allows me to use my shop vac attachments here. Okay. So the issues here is that whatever I decide to create needs to interface with this piece here on the left. That's the end piece of my Dyson vacuum. Okay, a little click interface. Here's an existing attachment that I have that I can actually use to reverse engineer some sort of adapter for this piece here, which is my shop vac attachment. This is a standard, I believe it's a 2-inch shop vac attachment. I'm going to be using this attachment rather than creating my own attachment, because if I can use off-the-shelf parts, it's going to allow me to do this quicker and a little bit cheaper as well. Okay, so at the design stage, this is where you open up SolidWorks and start designing your solution here. So I just created a short little video that's obviously real-time speed, right? Now it's been sped up, I think, 10 times. And I'm creating the adapter that's going to allow me to interface with my Dyson vacuum. So what you can't see here is that I've got my calipers out and I'm got the Dyson attachment in my hand, and I'm just basically reverse engineering it. It is sped up, but this is the full process, so if anybody's interested in how I did it, you could probably slow this down a little bit. I mimicked the geometry as best I could. That wasn't really needed. I did need this little feature here as a registration mark, so the adapter couldn't slide or spin, but I didn't really need all the geometry on the top there. I kind of just prefer to look at it and have as close of a reverse engineer model as I could. So then I went through there and I started creating some construction lines and sketches that are representative of the diameters of the shop vac attachment, and also some PVC line that I'm going to use as an extension here. So all in all, that took me about 10 minutes to go through and create that on the CAD side. So I actually created 2 parts. The one on the right is the one you just watched me create. That's the part that's going to click into the hose on my vacuum. Okay, and then it's going to allow me to pop in this other piece on the left, and this other piece is an adapter that allows me to go from PVC size to shop vac size. Okay, so this is either going to click into the part on the right, and I will use the shop vac attachment right at my hand, or I'll have the part on the right going into a PVC pipe into the adapter into the shop vac. So you'll see a couple pictures here later. Some of the other parts that I needed in my model I did not want to create, so I checked some of these sites: GrabCAD, 3D Content Central, Trace Parts, just to check to see if somebody had already created them and uploaded them so I could download them. This is a real time saver if you remember to do this. There's people out there who are extremely proficient CAD users, and they spend a lot of time making models and uploading them for people to use freely, right? And so I was able to actually just grab this PVC elbow and a shop vac attachment that was the correct size from GrabCAD. If you haven't checked those out, check them out. You will not regret it, especially if you have a 3D printer. But even if you're just coming up with some assembly models and whatnot. So the next step here is to validate. And by taking the time to create accurate models and then assembling them, I was able to ensure the proper fitment between the components themselves and also the environment that I'm going to be using this in. So you can see in this image, I actually went through and I created a SOLIDWORKS weldment using the same I-beam profile that's in my house. And then I created a SOLIDWORKS assembly that had all the components I just created or downloaded. Okay, so you can kind of see how this this little 90-degree angle fits in with the adapter and the shop vac. There's my adapter at the bottom, and this is a close-up of how that's going to sit. So by doing this, I was able to judge the length of my extension here and ensure that using a 90-degree elbow here in conjunction with my 45-degree shop vac attachment is going to give me a good angle of attack on the beam. Okay, so this is something that I only did to kind of validate my design before I actually went through the trouble of printing it and going and buying the components here. Okay, so this was sort of a peace of mind step here, and also it was something that I wanted to show my fiance and kind of show off that I could do this, and she wasn't quite as excited as I expected her to be, but nonetheless I still think it's pretty cool. So the next step after validation, we'll go ahead and we'll say everything fit together and it looks like my solution is going to work. So the next step here is to actually prototype, and a prototype is going to be the final step of validation, right? Prototype printing is going to be something that we can use to not only test in the digital world, but I'll have something in my hands that I can compare to my other attachments, but I can actually click them up and it will become a functional prototype. And the test here is if it works, it passes validation, and if it doesn't, then I need to go back to the design stage and make some changes, probably to my measurements, right? Because they're only going to be so reliable with using those calipers. So the first step here is taking my SOLIDWORKS model and saving it out as an STL file, and then opening it either in Control Center, Insight, or Object Studio. Those three softwares are going to be the softwares that are used to process the STL files before printing on the Stratasys machines. So my two parts were actually printed on two different machines, the Fortis 250 and the Fortis 400. That means I processed the STL files using Insight. Right? I've got a little animation here showing a screenshot from Insight, and what I'm doing is I'm scrolling up and down through the layers, so you're looking at one tiny slice at a time, and you can see the toolpaths here. So blue toolpaths, like you see right there, those are support material toolpaths, and green are model materials. So you can see this is actually the vacuum adapter. You can tell by the shape of it. Right. So what I'm going to do here is I'm going to quickly switch into Insight, and we're just going to process a file very quickly. So all I've done at this point is I've opened up my STL file. So this STL file came from SOLIDWORKS. I saved it out from SOLIDWORKS, but an STL file could come from, you know, pretty much any CAD system out there: Inventor, Rhino, CATIA, NX. You can get an STL file out of SketchUp, Blender, pretty much every CAD program you can think of. So Insight's going to open up the STL file. We're going to make sure that we have the correct machine selected here. So it looks like I'm on the 250 right now. I could switch that to, say, the Fortis 400. Choose my model material. I did this out of ABS M30. I'm going to choose my support material, SR30, and choose my slice height. I can't recall what slice height I did. I believe I chose, because I was kind of crunched on time, I believe I chose 100 thousandths. Okay. I could have chose, if I was concerned about the precision or the resolution, I could have chose a lower slice height. But I really was crunched on time. The entire workflow here took place in about a day and a half. So I was concerned about the print coming out in time. So 10 thousandths it is. Okay. The next step is I need to orient the part in the way I'm going to print it. Okay. So what you're looking at here, you can see this. The grid is the XY plane. So I'd be printing it on its side like this, which it would print just fine. But what we would see is, one, it would need a lot of support material. The entire thing would be filled up with support material. And also on these relatively flat areas, as this rounds around and this slope becomes very shallow, you'll start to see evidence of the layers. So wouldn't be quite as nice of a surface finish as I want. So I'm going to go ahead and rotate it here. I believe I printed it in this orientation here. And this is going to reduce the amount of support material that I need, which is going to reduce the amount of time. Because the way these print is, it prints support and model only one at a time. So it will do 2 layers of model, and then it will go and switch, clean the tip heads, and come back and do 2 layers of support, switch tip heads, right? And goes back and forth. So if I have several layers of model material, model and support material, the tip change time can become significant. So I'm going to print it this way. At this point, I could hit this green flag up in the top left, and it's going to walk through all of the rest of the steps for me. That'd be a little bit too easy to show on a webinar, so I'll do it manually here. First I'm going to do is slice the model. So when slicing the model, we end up with our 10 thousandths of an inch slices. So between each of these slices is 10 thousandths of an inch. So we can see a full representation. And once we slice the model with an Insight, we're no longer working on the STL file. So the STL file drops away, and we're left with these slice curves. And these slice curves can be manipulated and grouped up and edited. Okay? So for example, if I wanted to widen the part, I could grab this slice file and I could change the diameter of it. Or I could change the diameter of all of these at the same time. I could delete these interior slice files, and all of a sudden this would become a solid. Okay? So there's some changes that we can make on the Insight level and get a print that's different than the STL file that we came up with. Next step here is to create some toolpath. So when I create the toolpath, it's going to take the parameters of the toolpath that I have set, which are here. So it looks like 20 thousandths contour width, 20 thousandths raster width. So a contour is this outside pass that's next to the curve, and then the raster is the interior curves. Okay, they kind of just fill space. And I can shade these toolpaths so you can get a good feeling for what this is going to look like. So now the toolpath is shaded. This represents the thickness of the plastic. Okay, so you're actually getting a visualization of what the plastic would look like. These outside are contours, this inside is a raster. Okay? And what I'm going to do is I'm going to step through this slice by slice. And you can see as I go up, the rasters are flipping 90 degrees from each other. That's going to give us the best chance of a part that's very well fused in terms of the layers being homogeneous. And I'm going to scroll up, and we're going to start to see the profile of this part change. So what I'm looking for here are small features that get lost. So like this case here, where all of a sudden, because of the width of our contours and the width of our rasters, we get a spot that's kind of void. Okay? Now, if I didn't have Insight, I would just have to accept this as a fact. But with Insight, we have a lot of control over our toolpath, so I can make some adjustments and try to fill that in a little bit better. I might do that by changing my part raster width to, say, 16 thousandths. Let's bump it down. And let's also bump down the contour width. So once I make those changes, it looks like my part interior style is solid. I'm going to keep that. But we could also make it sparse. That would save on some weight. Once I make those changes, I'm going to regenerate the toolpath. And let's just check to see if this is filled in a little bit better. It looks like it is. Okay. Another change that I might make here is that instead of just a single contour around, I'm going to add a couple contours. So I'm going to do multiple contours. And this will just give it a little bit thicker skin. And that'll give it more strength in the directions that I need it. 3 was probably too many. I don't want that gap in there, so maybe 2. I still want some raster. Yeah, I'm liking that. Okay, so now I'm going to re-slice this, but this time I'm also going to create support slices. And I say I'm going to create them, but really the software is going to do all the work for me. It's going to determine where I need support. So we saw that the red slices are model slices, the gray and the yellow slices are support slices. Okay, gray slices are supports that don't touch the model, and yellow slices are supports that nearly touch the model, and then if you look closely there's a green slice. Those are slices that do touch the model. Alright, so it did all of that for me. I'm going to regenerate the toolpaths. It's going to regenerate the model toolpaths, but it's also going to generate support toolpaths now. And I'll kind of do the same thing that I did with the model toolpaths. Is I'll go do a top view, and I'll just step through it and make sure they look okay. There's a little bit less oversight that you need for the support material toolpaths. Alright, I'm on the very bottom layer here now. Notice that it's all support, and that's because it will create a bed of support and then start to build model material up on that. It builds a few layers. So you can see the support material is very sparse right now, and it's also kind of zigzag. You can see that this would break away very easily because they're not connected on both sides, right? As I move up, now it starts to get solid. It gives you a nice, strong, and smooth bed to build your model material on. And then it starts to go to model material. So this is done now. Again, I could have hit that green flag and it would have gone through all of that for me. The only thing I would have missed out on are the changes that I made to the toolpaths. Okay? And that's really where the strength of Insight comes into play. Is we can look at the model, make some adjustments to the toolpath, and come out with more refined parts. We can also, I went through and I increased the number of contours to the entire part. I could have broken that up and increased contours on only certain curves. So a good example of that would be if I had a flange with some bolt holes. I could go through and just grab the curves for those bolt holes and beef them up, give them a larger skin. I might do that because I'm going to be bolting down through them, or I'm going to be tapping through them and I need some meat for my threads, or I'm going to be press fitting a bearing in there and I need some strength in the radial direction. So lots of different reasons why I might do that. So at this point I would open up Control Panel, and start sending this to the machine by building a job first, which is going to allow me to choose where on my build platform I want to place this. Place it anywhere on my build platform. I can copy them, these parts. I could build 6 of them or 7 of them if I wanted to. It's going to give me an estimate for how long it's going to take. So with 8 of these, it would take 35 hours to print. That's printing 18 3/4 cubic inches of model and 13 cubic inches of support. Right. If I deleted these and just printed one like I did, it looks like it was about a 4-hour print. Right. So when I'm ready to do this, I'd say build job. This would send this over to Ethernet to the 400, and I'd go hit start on the 400 once I made sure that it was ready to go. Right. So that's a quick peek at Insight, some of the strengths that you have available to you. So here's some shots of this printing on the 400. When we peek in close there, you can see that there's actually 2 tips inside. The one on the left is the model material tip, and the one on the right is the support material. Looks like it's printing model right now. Looks like I'm about 3 hours into the print at that point. This is once it's done. So you can see in my left hand I'm holding the build sheet, and on the right hand I'm gripping the part. And all I'm going to do is I'm going to peel that part right off the build sheet. This is a peek into the 250. The 250 was printing the adapter part. So I got a couple shots going along the process. I'm an hour and 20 into it, or hour and 20 left, and I'm 68% done. So that's about 4 hours. This is once it's done. So if you look closely at this shot, you can see this is still in the machine. It's fresh. There's some differences in appearance in the materials. The very shiny ivory material is the model material, and the little bit more dull and chunky material is white material is the support. So the support, I'm going to do my best to break some of it off, and then I'm just going to pop it down in the detergent bath to wash the rest of it away because it's a soluble material. So post-processing is anything that you do to the prints once they're off the machine. Depending on what you're using your print for, they might be ready to go right off the machine, or they might need a little bit of touch-up on the post-processing side. Types of post-processing will be support removal, which again, there's the soluble support, which you just dunk in a heated detergent bath, or the breakaway support, which is you're going to use your fingers and maybe some pliers to break away. Bonding is another type of post-processing, and this comes into play if you're printing parts that are larger than the build area of your printer. You either break them up on the CAD side or you break them up within the Insight software, and they're printed in parts and then bonded together later. So bonding can be done with a solvent bond. They can also be done with hot air welding or simple epoxy. The first two there can be purchased at, the epoxy can be purchased at Home Depot, Lowe's, any big box home improvement store. The solvent can be purchased at the same places, also places like Hobby Lobby or whatnot. Hot air welding is you're usually going to have a tool there that's going to be coming from either a local supplier or you bought it online. And the reason why you might choose one or the other is usually just strength or whatever you're comfortable using. You have some secondary post-processing steps that usually have to do with appearance, so things like painting. We can definitely paint parts, and I remember at the beginning of this webinar I showed a picture of a part that had been painted, that mouse. So these parts are sanded, puttied, and primered and painted just like you would any other painted object like a car. They can be sealed, usually with epoxy. They can also be plated, plating of all sorts, electroplating, hot dip plating. Plating will not only give you a nice shiny surface finish, but it will also seal the parts in most cases. They can be mass finished using, say, your vibratory bowls, your tumblers, using anything from ceramic media to corn cob, walnut, plastic cones, pretty much any media that you would use for your metal parts, you can use for your FDM parts. Okay, and I've been actually very impressed with some of the parts that I've seen come out of these mass finishing processes. So we have some Ultim 9085 parts here at the bottom. One has been polished, and that's on the left, and cut on the right. So, you know, right off the machine, especially with the Ultim parts, you can see a little bit of evidence of the layering, and also some seams where the print head moves up in the Z. So for an end-use part, they're usually finished in some way. Mass finishing is a great way to do it if you have the equipment and if you have enough parts to justify it. These can also be vapor smooths. So Stratasys has a product called the Finishing Touch Smoothing Station. And what this machine has going for it is, you know, we can see that the lid and the door on the top of that machine there, that opens up. And when you open it up, it exposes just kind of an open area. At the bottom of this, you have a bath solvent, or a solvent bath, I should say. And that's heated up to the point where the solvent starts to vaporize. Okay? So what we do is we open up that lid and we drop our parts and just kind of suspend them in the vapor. Okay? It might be a single part, it might be a whole chain of parts. And we let the vapor just sort of melt the outer skin of this part. So this is a part that is right off the machine. I mean, like I just mentioned, you do see evidence of the layering, right? This is a part that went through about anywhere from 10 to 25 seconds of vapor treatment. So they held the part in the vapor and they let the outer skin melt, and then when you pull it out of the vapor, it will refuse and you get almost a glass-like surface finish on there, and it's very simple to do. So post-processing for my parts was pretty minimal. We can see a close-up of the bottom of one of my parts. I have that support material that this was printed on, right? So I just need to break that away. It looks like there's a little bit of a goober there around the diameter of the part, so I just hit that with a little piece of sandpaper. Any of the support that I couldn't break off, I let the bath dissolve. Right? I let it sit in the bath for probably a couple hours. The nice thing about the bath is that it's very hands-off. I can just drop it in there and come back whenever I'm free. This is opposed to the polyjet technology where the cleanup with the water jet is very hands-on. So it takes less time, might be 15-20 minutes for a part, but it's 15-20 minutes I'm standing there at the station, as opposed to the detergent bath where I just drop them and go on my way. So the last step in the validation process is to actually test the parts. We're going to test them for fit and function. Right, so here's the parts once they've been cleaned up. Again, the cleanup was very minimal. I might have touched it with a piece of sandpaper here and there and just melted out the support material. Here's my adapter next to the actual Dyson attachment. So you can see I did my best to really mimic the shape. This is how it's going to click into the vacuum. So on the right hand side there's my vacuum hose. In the middle there's the adapter there, so you can kind of get a good sense of how that's going to click in. That bottom ring on the adapter clicks in, and then that middle feature there is just a registration mark here that keeps it from spinning. So that's all clicked up. That clicked. It wasn't perfect actually. I had to. It didn't quite slip in as nicely as the injection molded part from Dyson. I had to push it in a little bit with a little bit more force. I think that's because my click ring was maybe 1/2 millimeter too far. Okay, so if I were to reprint this, I'd probably move that that ring that the button clicks into up about 1/2 millimeter, I would say. and that'd make it perfect. Other than that, this was a good prototype. And really, I shouldn't say other than that, because of the fact that I found something wrong with my design, that makes it a good prototype, right? That's the whole point of a prototype, is that you're testing it for fit and function and whatever you need out of it, and you're not really intending for that to be your final design. You might go through one iteration or 5 iterations. Luckily, I have 3D printing, so I can go through 5 iterations to really fine-tune your part and come out with the best part. Here's how the upper half is going to look. So on the right-hand side, I've got some PVC pipe and a PVC elbow. In the middle, I have my printed adapter, and on the left, I have my shop back attachment. And those all fit together just dandy. So after I assembled those all together, the final test was actually to take the assembly and turn the vacuum on and run some air through it and test how it works. And you can tell from this picture that it works in the sense that everything fits together. You'll probably just have to take my word for it that it was able to clean the beams. So I was actually really happy about this. I think my fiance was more happy about it. And I think I can safely say that I'm probably the only person in the world that uses shop vac attachments on his Dyson vacuum. So what's next? I mean, we went through the functional testing right there at the top. Obviously, the first step is I'm going to vacuum the beams. Right, that was what this is all about. Okay. Then I might consider some design changes. I ask myself, how can the design be improved? And what features might be added? If there are improvements to the design, I would cycle back through the design process like I mentioned there. And then finally, I'll assess the business potential. You know, this was a proof of concept. Was my solution the best solution? Sort of assess the commercial viability. Would my solution work for others? In this case, I think probably not. There's probably not a huge market for people using shop vac attachments for Dyson vacuums, but you know, who knows? If I decided that there was, then I'd continue on with the rest of my solution development cycle, the documentation and the manufacturing. Right? So the conclusion here, I was able to use SolidWorks and 3D printing to help me move through the first 3 steps of that product development cycle very quickly and easily. I mean, you watched some of my work on the CAD side. You saw the steps that I went through on the 3D printing side. In order to prepare for this webinar, I really did all of those steps, and I went from concept to vacuuming my beams within about a day and a half. I'm very motivated by deadlines, so I got it done very quickly at the last moment. I couldn't have done that any other way without 3D printing. So 3D printing was an excellent choice for my prototyping needs because, like I just mentioned, very quick turnaround time. My prototype was functional and it was very inexpensive. Okay, and I think those 3 themes are going to be themes that show up and they recur throughout all of your prototyping needs, no matter what industry you're in. You might be in aerospace, automotive, you might be in agriculture, or all sorts of industries. 3D printing is going to be lending itself to prototyping needs in all of them. Okay? So, at this point, we'll take questions and comments offline. My name again is Tyler Reed. You can reach me at treed@goengineer.com. If you guys are watching this later on YouTube, feel free to shoot me an email with any questions that you have. These are also good contact info to get in touch with us for Service Bureau parts. That would be Kirk Brown. Or to schedule times to come in and see the shop. That would be Kirk Brown or myself, or even Darren Warnick there. Darren Warnick is going to be the sales contact in Salt Lake City. Right? If you guys are watching this and you're in an area outside of Utah or Salt Lake City, places like Texas, Oklahoma, Louisiana, California, you're going to want to contact your local GoEngineer office, or you can contact us and we'll get you in touch with whoever you need. All right? So thank you for attending. I hope this has been somewhat informational for you. I know it was for me. I learned a lot going through the process, and I was really impressed with how quickly I was able to go through it. And having stepped through it one time, I envision myself going through it many more times because it was so simple, and I ended up with a product that is unique to me and serves a purpose. So thank you again.